Okay, let's talk about an equation called the Arrhenius equation. So the Arrhenius equation allows us to look at how temperature impacts the rate constants. So you've seen in a lot of the examples that we've been doing so far, you're given a rate constant and then it says at 25 degrees Celsius because that's the rate constant at that temperature. We know that temperature increases the rate of a reaction. So what happens if we change the temperature? How does that change the rate? So the Arrhenius equation allows us to look at that. So you're going to see the Arrhenius equation is the natural log of K2 over K1 equals the activation energy over R times 1 over T1 minus 1 over T2. So this might look a little bit familiar to you because this is the equation that we also used when we were talking about vapor pressure. We were looking at temperatures and vapor pressure and heat of vaporization. We're not looking at heat of vaporization and temperature. We're looking at rate constants and temperature. So this would be the K1 and T1 would be initial temperature and rate constant. K2 and T2 would be final rate constant and temperature. Activation energy, remember, is usually given in a unit of kilojoules per mole. R, remember what R we're going to be using, 8.3145 joules per mole Kelvin. So one of these needs to be changed. It doesn't matter which, just make sure that you justify these. The rate constants are going to be in some unit of molarity in time, and then the temperatures need to be in Kelvin because our R is in Kelvin. So this is very similar to what we did, the Clausius-Clapeyron equation. It's the same form, it's just looking at different variables. So we're going to solve it the same way. So let's look at an example. So it says in a series of experiments, the decomposition of dinitrogen pentaoxides rate constants were determined at two different temperatures. So it says at 35 degrees Celsius, the rate constant was 1.4 times 10 to the negative fourths, and I'm just going to do seconds to the minus 1 so this doesn't look like it's another exponent. At 45 degrees Celsius, the rate constant was determined to be 5.0 times 10 to the negative fourth seconds to the minus 1. So this makes sense because as the temperature increases, the rate constant should increase because we know increasing temperature increases the rate of chemical reactions. This question is asking, what is the activation energy? And another question, what is the value of the rate constant at 55 degrees Celsius? So two questions, two totally separate questions that need to be solved totally separately. So the first thing I'm going to do is I'm going to use the Arrhenius equation to solve for the activation energy. Two, I'm going to plug the activation energy in with the new temperature, 55 degrees Celsius, to solve for the new rate constant. So two problems. So let's do this one first. First, let's solve for the activation energy. Okay, so I'm just going to plug everything in here. I'm going to say, okay, natural log of K2, 5.0 times 10 to the negative fourth seconds to the minus 1 over 1.4 times 10 to the negative fourth seconds to the minus 1 equals the activation energy, that's what I'm solving for, over 8.3145 joules per mole Kelvin times 1 over T1, 308 Kelvin, minus 1 over 318 Kelvin. Don't forget to convert your temperatures to Kelvin. So we're going to rearrange this whole thing. You should get 1.23, and then when you rearrange all of this, you should get an activation energy of about 1.0 times 10 to the fifth joules per mole. We can actually just leave this as joules per mole, and then when we use it here, we won't have to convert anything. Or you could say 1.0 times 10 to the second kilojoules per mole. Two significant figures because my question has two significant figures. So that's the first part. Solve for the activation energy. Now the second part says what is the new rate constant at 55 degrees Celsius. So now I'm going to use, let's see, I'm going to use T1 and K1, and then I'm going to use 55 as my new T2 and solve for the new K2. So that's what I'm going to do down here, using the activation energy that I just solved for. So I'm going to say natural log of K2, what I'm solving for, 1.4 times 10 to the negative fourth seconds to the minus 1 equals what I just decided over here. So I'm going to say 1.0 times 10 to the fifth joules per mole over R, 8.3145 joules per mole Kelvin times 1 over T1, 308, minus 1 over T2, 328. Now I'm going to rearrange all of this, solve for this side, exponentiate to get rid of the natural log, and you should solve for K2. You should get something like 1.7 times 10 to the negative third seconds to the minus 1. So this is the rate constant at the increased temperature. So again, anytime that you can think about what your answer means and make sure that makes sense, that would solve you from getting a problem wrong from just a calculation error. So from this, even from the first temperature to the second and now the third, the temperature is increasing, which means the rate constant should be getting faster and faster, which it is. This is a bigger number. So this is the Arrhenius equation, same exact equation as the Clausius-Clapeyron equation that we used for vapor pressure. Instead of looking at vapor pressure versus temperature, we're looking at rate constant versus temperature. Make sure that your units for activation energy and R are the same. Make sure that you convert temperature to Kelvin.